So we are starting today looking into chapter 15. Chapter 15 is all about acid-base equilibria. And so what we're taking, again, we're taking those concepts from General Chemistry 1 and blending them with what we just saw in equilibrium in chapter 14. And what should happen by the time we are done with this, middle of next week, is we should kind of have a better understanding overall of what it means to be an acid, what it means to be a base, and how equilibrium kind of allows us to explain some of the properties that we glossed over in Gen Chem 1. So we're going to start today by largely reviewing things that we learned in General Chemistry 1, so in Chem 105. And the first thing that we are going to look into is this idea of the acid-base theory. So in Chem 105, we talked about two different theories of acid and base. We talked about Arrhenius theory. This was the theory we used to help identify acids and bases. Acids start with hydrogen, bases end with hydroxide. And so when those acids get put into water, that hydrogen ion pops off of that acid, and that's what makes it an acid. And when we put those bases into water, that hydroxide ion pops off of that base, and that's what gives it its basic qualities and its basic properties. But we also realized very early in Chem 105, hold on a second, wait. There are substances that we know that don't begin with hydrogen, yet act acidic. And there are substances that we know do not end with hydroxide and yet are basic. Is there any room to expand Arrhenius theory? And so that's when we started to bring up the idea of the Bronsted-Lowry theory. Bronsted theory took us to looking for the movement of hydrogen. Acids give up hydrogens and bases take them in. And so when we looked at something like ammonia, which we knew had basic properties, we could say, okay, ammonia as a gas maybe isn't so basic, but when we throw it into water, it grabs one of those hydrogens off of water, and now it is basic. And so that's what we kind of settled on as kind of our, okay, this is where we're going to stop our defining of acids and bases in Chem 1. We looked at the movement of protons, the movement of hydrogen ions. Acids lost them and bases took them. And what we could see in Bronsted theory is that it was basically a better explanation than Arrhenius theory. Everything that Arrhenius theory did fit into the Bronsted theory as well. So when we talked about things like ammonia, we couldn't identify the ammonia as having a hydroxide to lose. But we know that when it dropped into the water and it took that hydrogen off of the water molecule, take a hydrogen off of a water molecule and you're left with hydroxide. There's the hydroxide that the Arrhenius theory was looking for in the first place. We can identify it as a base. What the Bronsted theory also allowed us to do is what it allowed us to identify that acid and base reactions were coupled. They were paired with each other. When an acid reacted as an acid, the other thing that it reacted with acted as a base. So if I had hydrogen chloride here, and this hydrogen chloride was going to give up its hydrogen to the water, we would identify, okay, that is definitely acidic behavior. But by the mere act of taking that hydrogen, that means that the water was acting in a basic way. Under Bronsted theory, I couldn't have one without the other. Kind of like when we looked at redox, you couldn't have oxidation on its own. If there was oxidation, there had to be reduction as well. You couldn't have one without the other. If something's giving up a proton, that proton has to land somewhere. And similarly, we could see the same kind of thing with bases. One of the hydrogens pops off the water and goes to the ammonia. That means that the water is acting as an acid and the ammonia as a base. And what this generates for us is a couple of things. First of all, we can always identify acids and bases based off of these properties. All I need to do in looking at a chemical equation involving one of these is simply to monitor the movement of the protons and figure out, okay, is this an acid or is this a base? But what we also would see under this theory is that there are certain substances that are actually capable of acting as acid or as base, depending upon their situation. I put water with a substance that is more acidic, the water acts like a base. I put the water in a situation with a basic substance, it acts like an acid. We have a name for those kinds of compounds. We call them amphiprotic. Now, water is the most common form of an amphiprotic substance. But what we will find in this semester and in this chapter rather, is that there are others, and most of them are going to fall along the lines of ions from polyprotic acids. So things like the hydrogen carbonate ion, where if I add a proton to it, it becomes carbonic acid. If I take that extra H plus away, it becomes the carbonate ion. It is perfectly stable going either direction. It just depends upon the acidity or the basicity of whatever we put with it. We can say the same kinds of things for the dihydrogen phosphate ion or the bisulfate ion. And there are others as well. These are probably the most common three. So this amphiprotic nature does lend itself to some really interesting properties depending upon the environment that we put these substances into. What we can also recognize is that by pairing up these acids and bases, we always focused on the forward direction in Chem 105 because we really didn't talk at all about reversibility. But now we can. And so if I look at a reaction like this, I see, okay, in the forward direction, this hydrogen is going over here. So this must be my acid, and the water must be my base. But if I look at the reverse reaction, I can see that in the reverse reaction, the hydronium ion here, H3O plus, it's giving a proton away to turn the X minus back into HX. So it's acting like an acid. And the X minus ion is acting like a base. What this creates for us is something called a conjugate pair, where I can look and say, oh, hey, wait a second, this is kind of cool. The water and the proton, or excuse me, the hydronium ion, these two are cousins. One hydrogen ion apart. They act as an acid-base pair. They're called a conjugate acid-base pair. As water, in this particular situation, it acts as a base. As hydronium ion, it acts as an acid. And I can also see that same conjugate nature for the HX and the X minus. They are one proton apart from each other. And one of them is acting as an acid, and one of them is acting as a base. These are known as conjugate acid-base pairs. And every reaction that is acid-base in nature will have two sets of these pairs, where on one side of the reaction, one of the conjugates is acting as an acid, and on the other side of the reaction, that conjugate is acting as a base. The conjugates never act only as acid or only as base. One will always be acidic, one will always be basic. But they will always be one proton apart from each other in this reversible reaction. And identifying these pairs is important because what we will find is that the properties of strength that are associated with one directly correlate to what we will associate with the other. They'll correlate actually in an inverse relationship. The stronger one of the conjugates is, the weaker the other one is going to be, and vice versa. So again, book definition of conjugate acid-base pairs. What we're looking for are species that are separated by a hydrogen ion to each other, where one of them is acting as a base and the other one as an acid. By convention, we tend to label the species on the reactant side as acid and base, and the species on the product side as conjugate acid and conjugate base. So we would call HX the acid and X minus its conjugate base. We would call water the base and the hydronium ion its conjugate acid. Now, it's not incorrect to call them both conjugates of each other. But generally speaking, if we are identifying them in a reaction like this, that is usually the terminology we use, is we'll look at things from the perspective of the forward-facing reaction. So one of them is acidic, one of them is basic, and then we have their conjugates on the other side. And you can see that terminology here in action, this time with the reaction of nitrous acid with water. The nitrous acid is our acid. The nitrite ion is its conjugate base. The water is our base. The hydronium ion is its conjugate acid. All right, let's do a practice exercise together here. I've got the bisulfite ion, HSO3 negative, reacting with water to make sulfite and hydronium. The trick to this is identifying which way the hydrogen ion is going. So if I'm looking in the direction of the hydrogen ion, I can see, okay, the water turned into hydronium, so that meant it added the hydrogen. So the hydrogen ion must have gone from the bisulfite to the water. That means that this is acting as an acid and this as a base. Now we just need to identify the conjugates. Bisulfite ion minus H plus would be sulfite ion. So that must be the conjugate base. And that would mean that the hydronium is the conjugate acid. Now we can check ourselves here just to be sure. Does this conjugate acid act like an acid in the reverse direction? Well, we can see that it is giving a hydrogen to the sulfite ion to turn it back into bisulfite. So yes, it is acting as an acid. The sulfite is acting as a base. We've labeled the conjugates correctly. For this second one, we've got bisulfate ion, HSO4 negative, reacting with the carbonate to make sulfate and bicarbonate. Once again, identification here, looking for any clue to give me an idea of where the hydrogens are going. I can see that to go between this conjugate pair, I had to have lost the hydrogen ion here. That would mean that this is the acid. So the hydrogen ion is leaving the bisulfate and heading to the carbonate. Now, another dead giveaway here is the fact that the carbonate has no hydrogens to give. So under that definition, there's no way it could have been an acid. The only thing that it could be is a base. So that's the acid, that's the base. We've already identified the conjugates. So this would be our conjugate base. This would be our conjugate acid. We could double check ourselves just to make sure. Does the hydrogen go from the bicarbonate to the sulfate? And we can see that it does. All right, any questions about Bronsted theory, conjugate acid-based concepts? Okay, so let's continue our review then. Let's talk about acids and bases. Now, in Chem 105, we really only talked about strength from the perspective of memorization largely. These are the strong acids, these are the strong bases, memorize them, everything else is weak. That's more or less what we said. And so just as an identification exercise, again, those are your 7 strong acids: the hydrochloric, hydrobromic, hydroiodic, nitric, chloric, perchloric, and sulfuric acids. And on the flip side, your common strong bases, these were your alkali metal hydroxides and your heavy alkaline earth hydroxides, starting with calcium. So no magnesium, no beryllium on this list. Now, these substances all have conjugate acids or conjugate bases. But we have to remember that the inverse relationship that exists basically tells us that the stronger the acid is, the weaker its conjugate is going to be. The stronger the base is, the weaker its conjugate is going to be also. And so when it comes to conjugates of strong acids and strong bases, what we will find is that the conjugate bases of those strong acids have practically no basicity. If I drop a chloride ion in water, chances are pretty good it's not going to do anything to the pH of that water. Same thing with nitrate ion. Same thing with perchlorate ion. On the flip side, the conjugate acids of these hydroxides are actually the metal ions themselves. And we're going to find the same problem. The stronger that base is, the less acidic those ions are going to be. And so sodium ion in water, no effect on pH. Potassium ion on water, no effect on pH. Now we can rank them because there is actually a hierarchy in terms of acid strength and base strength. And as far as acid strength is concerned, that hierarchy is largely based on the nature of those conjugates. But there are some important things that we can note. So first of all, up here in the top of the acid strength list, you have all of your strong acids, your hydrochloric, your sulfuric, your nitric. In between there, you've got the hydronium ion. Hydronium ion is really present as an acid only in the fact that it's what those strong acids react with, react to make. In your weak acid, there is a ranking system here. The ranking system of those weak acids is based off of something called Ka. Now, we already know what capital K is. It's the equilibrium constant. The A value there is just a reference to the fact that we are talking about the equilibrium of an acid as opposed to anything else. And so generally speaking, the bigger that value is, the higher up on that list it's going to go, the stronger the acid is going to be. And similarly, for weak bases, we have a value called Kb, the equilibrium constant for bases. That tells us essentially the same thing. The bigger the value of Kb, the more basic the substance is. So as we climb up this tower, what we're going to notice is that as our acidity increases, the basicity of the conjugate decreases. So base strength goes in the opposite direction. Hydrochloric acid is strong. Chloride ion is so weak that we don't even consider it to be basic. Nitric acid is strong. Nitrate ion is so weak, we don't even consider it to be basic. Hydrogen fluoride is a weak acid. Fluoride ion has some basic character to it. One other important thing to notice here. When we looked at polyprotic acids in Chem 105, we generally assumed that those acids broke off entirely. So when sulfuric acid reacted with whatever it reacted with, it would drop both of its protons in the chemical reaction. That was always what we assumed. What this tells us actually is that's not really the case. Because if it were the case, then what we would see is that the hydrogen sulfate ion would be a strong acid just like the sulfuric acid is. But it's not. Here it is with the weak acids. So when it comes to polyprotic acids, and we'll talk about this more next week, that deprotonation process, that dropping of hydrogens as it reacts with water or as it reacts with a base, is going to happen in a stepwise fashion. So for sulfuric acid, that first deprotonation, that conversion from sulfuric acid to the hydrogen sulfate ion, that is a strong conversion. That one is a one-way street. But that second conversion between the hydrogen sulfate ion and the sulfate ion, that one's actually a reversible reaction. And we're going to be able to track it, monitor it, calculate with it using an equilibrium constant. All right, let's try a problem for ourselves here. So using this chart, what I want you to do is you've got a list of ions. I want you to put them in the correct order based on decreasing strength. So start with the strongest conjugate base and dial it down to the weakest conjugate base. All right, let's see how we did. So we need to put these in the correct order from strongest to weakest. So hydrogen ion was one of them. Acetate ion was another. Hydroxide was another. Fluoride and chloride were there as well. So hydrogen ion, or excuse me, hydride ion, H- would have been first, then hydroxide, then acetate, then fluoride, then chloride. Is that what we did? Okay, that's the most popular order. And that's also, like I said, the correct order. All right, so let's go ahead and take a break right there. Come back in about 10 minutes and we will take a look at factors that impact strength of acids.